Hi folks, welcome back to Physics with Captain Rod. I'm making this one to help you Physics 109 students out with numbers 4, 5, and 6 on your Unit 2 homework. So number 4 is about a person standing in an elevator, and the person is standing on a bathroom scale or some sort of scale that tells you the weight. So here's my super crude picture of that. And it says in the problem that the scale reads 751 newtons when the elevator is at rest. So that's important to realize that, right, the velocity is 0 and not changing. So the weight of the person is 751 newtons. And weight is equal to mass times gravitational acceleration, mg, where the g is the 9.8 meter per second per second. So this is just a matter of putting in the weight and the value for g and solving for the mass, and you'll get a number out of that in kilograms. All right. Parts B and C, though, starts add a little bit of complication here. So part B, it says if the elevator is accelerating upward with an acceleration of 3 meter per second per second. And again, yours may be a different number, but it'll be close to that. And what we're going to do is, this is called a force analysis, or also called a free body diagram. If we draw force vectors acting on the person, the weight of the person acts down. And we would call that like W for weight. And that's going to equal the 751 newtons. And that force is there whether the elevator is accelerating or not. Okay, the other force that acts on this person is the force between the scale and the person's feet. And that force is acting upward on this person. So in our force picture, we would draw it like this. And forces like that are sometimes called normal forces. I'm going to go ahead and put N for normal. And the reason they use the word normal is just kind of a fancy word for right angle. And you'll notice that this force is perpendicular to the soles to the bottom of the person's feet. And the bathroom scale actually measures this one, is what it actually directly measures. Right? Now, when you say Newton's second law, right, is net force equals mass times acceleration, the net force is the sum of these two, right? And that's what's referred to as a vector sum, right? Vectors are quantities that have magnitude and direction. So this one is up, so we normally would assign a positive number to that. And this one is down. So the net force, based on our picture, is equal to the vector sum of these two, which should be N minus mg. And again, this one is minus because it's down in our picture. And by Newton's second law, that's equal to ma. Now, if I could go back and talk about the first part of the problem, when I was talking about this stuff from here up, I was inherently already using this. I just didn't mention it. I probably should have. But when the elevator was still, this was 0. And the normal force is what the scale actually measures, and it is equal to the weight when the acceleration is 0. Now, when the acceleration is not 0, like in part B, now the acceleration is equal to 3 meter per second per second. So what you want to do now is put in the values that we have for the weight, the mass, and the acceleration. And then when it says, what does the scale read? The scale measures this, the force that I'm calling the normal force. And that'll hopefully get you through part B. For part C, where it says the elevator moves with a steady speed of 6 meter per second. So if our speed, or let me call it our velocity for a minute, is 6 meter per second, and it says steady, that means the acceleration is 0 because this is not changing. This equation is really still valid, except now you're going to put a 0 in for the acceleration. And then put the weight in, which again is still 751. That's not changing for the entire problem. And then you could solve for the normal force. So this one's kind of a long problem. It tends to give people a lot of trouble, and that's okay. I'm going to go ahead and call that a day on this one and move on to the next one. All right, number 5 is about a jet. So you might want to start with just a quick picture of a jet. All right, well, doesn't have to be a great picture. I might want to have to label that even. All right, and the mass of the jet is given in the problem. In the problem that I'm looking at, it's 4475 kilograms. Yours might be different. So, you draw a quick picture and write down the relevant information. It says the engine produces a thrust equal to 60,200 newtons. So that's an example of a force. So we can draw what's called a force vector like that. And it doesn't matter horizontally where you put this, by the way. Like this force vector can go really anywhere along this line. These force vectors have what's called a line of action to them. I'm just going to leave it like this now. And then we're going to write out Newton's second law, which says force equals mass times acceleration. And the force is a number that's given in the problem, and the mass is given in the problem, so then you can solve this for the acceleration. And that'll get you part A. Part B, where it says, what is the speed after it accelerates for 7 seconds? Well, you might want to start out by writing acceleration is equal to change in velocity over change in time. Right? This is how acceleration is calculated. You're going to get the acceleration from here, and they gave you a delta t in the problem. In the one I have, it says 7 seconds. Yours might be different. Then you're going to solve for this, the change in velocity. And you also notice it says start from rest. So if you're starting from rest, basically whatever your change in velocity is, that's going to be your new speed. And then part C, how far does the jet travel during the 7 seconds? So that's a question very similar to Unit 1. And if you've watched my video content for Unit 1 here, how I usually have people kind of analyze that is you draw what I call a velocity graph, velocity against time. That's one of the most useful graphs you can come up with to kind of look at the motion of an object. So at t equals 0, this thing isn't moving yet. So the first point on the graph goes here. And then 7 seconds later, right, you're going to get the final speed. You're going to know that number. So that's going to go maybe up here somewhere. It doesn't matter like this distance, how far you draw it. That's just kind of a sketch here. Okay, then you connect the dots. All right, and again, this distance on the graph, you're getting that from up here, from part B. And then hopefully we remember how to get our displacement here. Our delta x, right, that's our displacement, is coming from this area right here, and it's a triangular area. So 1/2 the base times the height will tell you how far that thing went. So that's enough for number 5. That should get you moving right along. Whoops. Darn it. Oh, there we go. Number 6. Let's see. The maximum acceleration of a fist during a karate blow is measured to be 2430 meters per second squared. You may get a different value. So we're talking about, that instant in time when the fist is in contact with something and it's slowing down. It's going from some sort of high speed to 0. And just real quick, if I were to draw a velocity graph for the fist, it's going from some number very quickly to 0. So this is some sort of time frame, a delta t, and this is your change in velocity. And anyway, let's see. In the problem, the acceleration is a given number. Mine says 2430 meters per second. And the mass of the fist is given in the problem. Mine says 0.6 kilograms. So we're going to write these values down. And then we write out Newton's second law. Net force equals mass times acceleration. And the mass is given in the problem, and so is the acceleration. So you can just find a value. Now, I should actually add this to it. If we call this way positive, which I did when I drew this velocity graph, you'll notice this has negative slope. And remember that Acceleration is change in velocity over change in time, and that's equal to slope of a velocity graph. So really technically, you're going to want to put minus 2430 in, and you're going to get a negative number for the net force. And all the negative number means is that the force is to the left on this person's fist. And part B is kind of a conceptual question. What is the maximum force on the concrete block? So that's about Newton's third law. And remember that Newton's third law is forces always appear in pairs. It's kind of a conceptual question, so I don't want to answer that now. Hopefully that will get you through these three problems. Have a great day.